Okay, so today will be mostly on screen, and I should say I'm still trying to perturb the Heisenberg-Knot invariant, and the main point is not to perturb the Heisenberg-Knot invariant, but to learn how to do perturbations, because the thing we will really want to perturb will come later. So once this is done, we will have another chapter of theory about another class of algebras that give invariants. Okay, so let me remind you where we were. So we have the two most interesting tensors for the Heisenberg algebra. So the multiplication, well, I call it tensor, the generating function of multiplication. We've seen this formula several times. I don't want to say anything more about it. And then the R element, which is e to the uppercase t minus 1, pi minus pj xj. And this time I want to add a perturbation, R prime. And R prime, in general, will be a power series in a new parameter, epsilon. And I wanted to start with epsilon to the power 1. So it will be a sum as k goes from 1 to something. Epsilon to the k, r number k. So I wanted to start with k to the 1 because I want it to be small. Okay? So it has to start with having a power of epsilon. And then, well, in principle, it's an infinite power series, but everything I want to do is to compute at the end, and there will be no kind of patterning of this power series. It will not become into a closed formula. So I just chop it at some fixed k, and the maximum k I will call $k. Sorry for mixing Mathematica and mathematics notation. Anyway, let me also remind you that the composition of two generating functions is given by, well, you multiply them and you apply this infinite order differential operator, sum over all indices in the middle set, B, of differentiation with respect to the Latin letter corresponding and the Greek letter corresponding. And then, inspired by this, we define, and so up to this definition, Greek and letter played separate roles. And in fact, the Greek letters are psi and pi, and the Latin letters are p and x. But from here on, I simplify matters, and I just have one class of letters, and they're called z. Okay, and I define f colon expression to be, so where f is a matrix and e is some functional, some power series in my Latin variables, so Greek, in the z's. So I define this to be e to the 1/2 sum over all the variables in v. So over u and v running in the variables of b, fuv times derivative with respect to mu, the u derivative with respect to v applied to epsilon, and then set all the variables to 0. So, by the way, I will sometimes call this the Laplacian. I already did, but basically it's like the Laplacian, right? It's a symmetric form applied to its second derivatives with some symmetric form between them. And then, similarly, bracket f colon e is the same, but without substituting z to 0. And here is a note I didn't make before. These two definitions are essentially interchangeable. So if you know how to compute one, you know how to compute the other, and vice versa. So if I give you techniques to compute one, I also gave you techniques to compute the other. And the reason is that, if you know the f colon e bracket, you just substitute all the variables to 0, and you get f colon e triangular brackets. And the other way around is also not very hard. So basically, the triangular bracket is about complete gluing. So you complete glue the things in f du dv into the variables that appear here. But if you know how to completely glue, you could do partial gluings as well by substituting, so replacing every z here by z plus z bar. Z plus z bar. So now you get a new where the z bars. So basically, what I really mean is every zi get replaced by zi plus zi bar, where zi bars are a new set of variables. And then, after making these substitutions into E, you do complete gluings into the z's. And then substitute the z's equal to 0. But that still leaves you the z bars outside, so you get the result of incomplete gluing. So basically, the square brackets, but with the substitution where you rename every z variable z bar, is equal to, first you do the substitution zb is zb plus z bar b, and then you do complete gluing of the z variable that leaves the z bar, that leaves some of the z bars hanging outside. Okay. Okay, and the final thing is not the final thing, further review thing. So if I want to do incomplete gluing of things that are exponentials. So the inside is an exponential, and I want to write the output as the exponential of z lambda. So z lambda is log of this incomplete gluing. Then z lambda satisfies a differential equation. So z0 is simply E, and the derivative with respect to lambda of z lambda is given by the formula written here. We derived it earlier. And this is sort of like a heat equation. So basically, the derivative with respect to lambda of z lambda is the Laplacian applied to z lambda, but it's perturbed and made nonlinear. Okay, and then last time we talked about two lemmas, and now I want to complete the discussion. So, lemma number one. So in fact, I think last time I gave them in the opposite order, but that was probably a mistake. So, lemma number one, if you glue f to an expression, any expression, times a Gaussian, you can cancel the Gaussian out, and instead, well, then you get some determinant, and then you just need to glue to the expression, but the gluing matrix becomes different. And again, we had a discussion of that, and the picture is kind of clear. So gluing f to g and then an arbitrary expression is just gluing to this expression, but you're allowed to do loops between the f and the g. So the gluing matrix becomes this geometric sum. And then lemma number two, so if you have an expression multiplied by something linear in the z's, then gluing it with matrix F gives you a quadratic outside, and the gluing after you've made a certain substitution. And again, we did it last time, so I'm not, unless there are questions, I don't want to say anything about it. But the point is that after you apply these two lemmas, you can get rid of, so I mean somehow, right, when you multiply L by M, so the things we want to do, to work with, you're going to get something quadratic in all the variables, plus a perturbation. Where's the perturbation? Here's the perturbation. Potentially a perturbation. A quadratic is quadratic in all the variables, but we're gluing only the variables in B. So if you restrict the quadratic in all the variables to the variables in B, it becomes quadratic plus linear, right? So a quadratic in X and Y has a quadratic terms in X, but also a linear term in X. And these two lemmas tell you how to get rid of the quadratic part and and the linear part. And at the end, you're left with gluing with a new matrix, into something in which you've gotten rid of the quadratic and the linear. So it's only the perturbation. So that's the point of these two lemmas. And now I want to deal with gluing with the perturbations. So I actually have no choice but to go back to this synthesis equation, so this equation, and to solve it. So, but you see, I'm solving it as a power series in lambda, or I wish to solve it as a power series in lambda. So I write z lambda as sum of z bracket m lambda to the m. And again, sorry for mixing mathematical notation and mathematics notation. And then, and then the equation becomes, so basically, how can I get a term proportional to lambda to the m in this equation? Right, so I write it as a power series in lambda, and then I make it into separate equations, one for each power of lambda. So how do I get a term proportional to lambda to the m over here? I either look at the part of z lambda, which is of, that has lambda to the m plus 1. So I look at zm plus 1. And differentiate it with respect to lambda, so I get m plus 1, z of m plus 1. Or I look at the power of lambda to the m, or the coefficient of lambda to the m over here. The coefficient of lambda to the m over here comes either from here, where you get simply the lambda to the m can only come from the z lambda here, so it's the coefficient is zm, and you have to differentiate it with respect to u and v. Or you get it from here. So to get the power of lambda to the m from here, you can either get it by getting lambda to the j from here and lambda to the m minus j from here. So you get sum over j of the derivative with respect to u of zj plus the derivative with respect to v of zm minus j. So, and then z0, when lambda is equal to 0, z0 is just z sub 0, which is also e, the e we started from, right? z0 is e. So basically, this allows you to solve the synthesis equation iteratively, right? So if you know z0, then you substitute here m is equal to 0, and from z0 you get z of 1, and then you repeat. Okay? The problem with this is that you get an infinite power series in lambda, in general. And what I will show you now is that after you've gotten rid of the quadratic and the linear terms using lemmas 1 and 2, and in sufficiently good conditions, this becomes a finite power series. In other words, a polynomial in lambda. So you don't. So this becomes a finite process, and you can actually implement it. Okay. So I need I need several things. First of all, I want to tell you what is a docile power series. So a power series f in some variable epsilon, auxiliary variable, well actually it's the same epsilon as before, so the perturbation variable, and in many variables z. And z are, I mean including the z's that are not in the set B where I do the gluing. So the Greek, if you compare to category theory, it's the Greek and Latin letters that, so the zi, the zi, the zeta I, sorry, the xi, the xii, the pi, the pi of A, B, and C. So not just the ones in B, okay? So anyway, a power series like that is called docile if every monomial in it, this should be in it, not it. Every monomial in it has the property that the degree with respect to the z variable is less than twice the degree with respect to epsilon plus 2. Okay? Why this? Because it works. You'll see. Okay? So, in other words, a docile polynomial, a docile perturbation is a perturbation of the form, so epsilon to the 1, and then this is allowed to have to be multiplied by something of degree 2 times 1 plus 2, so up to degree 4. So maybe xi pi px, or maybe x to the 4th, or maybe pi squared x squared, I don't know, plus epsilon squared times something which could be of degree 6. So zeta to the cubed, pi cubed, or something like that. And in fact, you know, I'm thinking of the perturbations as beginning with epsilon, but you know, I could have started earlier and called it epsilon 0, and epsilon to the 0 here, what I can have here is at most quadratic in the variables, which is actually consistent with what I'm doing. Okay? The thing to note here is that if I crop at a finite degree, so if my $k, the maximal power of epsilon that I'm allowing myself to use, is equal to 2, then I'm dropping all the terms beyond epsilon squared, and then at the most I see polynomials of degree 6, and the space of polynomial of degree 6 is of dimension comparable to the number of variables to the power 6. So basically, because you have to choose 6 of the variables to make a monomial. So the space of docile polynomials is itself has in itself dimensions that grow polynomially. So as a power of k. So it's a relatively manageable space. And by the way, and back to the handout, I will short. So instead of writing every monomial satisfies the degree with respect to z is less than twice the degree with respect to epsilon plus 2, I'll just write it, the degree with respect to z of the function is less than twice the degree with respect to epsilon of the function plus 2. And when I write a thing like that for a power series, what I really mean is that this is true for every monomial in the power series. Okay. So, of course, there should be a claim here. And the claim is that the synthesis equation preserves docility. In other words, if E is docile, so if we start with a docile thing, then so is Z lambda. I think I have a grammar issue there. And therefore, so is the log of F colon e to the E. Okay? So, in other words, but you see, this is how composition is defined. So basically, if L and M are the exponentials of docile series, then their composition will be again the exponential of a docile series, and therefore finitely manageable. Okay? So I just have to prove this theorem. So I have to declare. So I have to prove that if E is docile, so if Z0 is docile, then Z lambda is docile, or in other words, every Zm is docile. Okay? But that's kind of obvious. So let's look inside this equation. So maybe I'll write this equation. Maybe I'll copy this equation to have it on a medium on which I can annotate. So the equation is Z m plus 1, you know what, I'll switch to math notation. No. So Zm plus 1 is equal to 1 over 2m plus 1 fuv the derivative with respect to u, derivative with respect to v of Zm plus sum over j derivative with respect to u of Z j derivative with respect to v of Z m minus j. Okay. And now I want to claim that if Zm is docile, then so is Zm plus 1. But again, that's obvious because let's look at the coefficient. So let's look within the coefficient of epsilon to the k in any of the terms above, in each of these terms, look at the degree with respect to z, with the degrees of the z variables. So, you know, every term here has a coefficient of epsilon to the k, and within it, let's look at the degree with respect to z. So this is the degree I want to know. Okay? But what I already have is that, okay, so all of these are just scalars. These are matrix elements, these are scalars, this is a rational number, so it's not, that does not contribute anything. Here I have the coefficient of epsilon to the k. So it has degree at most 2k plus 2, because Zm is docile. I'm trying to prove by induction that all the Zm's are docile. Starting from the fact that Z0 is docile. So by induction, I'm assuming that Zm is docile, so the degree here is less than 2k plus 2, minus 2 because I differentiate twice. So the degree here is less than 2k, in fact. And the degree here is, okay, so how can I get a degree, how can I get epsilon to the k from a product of two things? So I could get epsilon to the k1 from here and epsilon to the k2 from here, provided that k1 plus k2 is equal to k. And then, if I'm looking within the part of the within the term, the coefficient of epsilon to the k1, I look at the degree with respect to z, then it will be at most 2k plus 2k1 plus 2 minus 1 because I'm differentiating once. And from the second term here, I will get at most 2m minus j plus 2 minus 1, again because I'm differentiating once. And when you add these two things, sorry, not m minus j, 2k2. I'm looking at powers of epsilon, not powers of lambda. So 2k2 plus 2 minus 1. And when you add these two things, you get 2k1 plus 2k2, that's 2k. Plus 2 minus 1 plus 2 minus 1, that's plus 2. So this contributes a sum of two things whose degree is at most 2k plus 2. So the degree here is at most 2k plus 2, and that's what I wanted to show. Okay. So, okay. In the moral is later, everywhere, I can restrict my attention to docile perturbations, and then if I do that, I stay within that class. So somehow I get a limited space of perturbations within which to work. Okay, claim number 2. So restricting our attention now to the variables in B, then if the degree with respect to these variables, these are the variables that are actually active, which I actually contract. So if the degree with respect to this variable in the initial term, in E, is less than 4 times the degree with respect to epsilon of E, so by this I mean every monomial in E, okay? Then the degree with respect to this variable of z lambda is less than or equal to 4 times the degree with respect to epsilon of z lambda minus twice the degree with respect to lambda of z lambda. So in other words, if you write z lambda as a power series of in all the in the zb's and in lambda and in epsilon, then every monomial satisfies a certain inequalities of degrees. Before telling you why this is true, it's true for trivial reasons, but before telling you why this is true, why is this useful? It's useful because it means that well, since this number is always greater than or equal to 0, it means that 4 times this is greater than twice this, and therefore this, the degree with respect to lambda of z lambda, is less than twice the degree with respect to epsilon. So the degree with respect to lambda of z lambda is less than twice the degree with respect to epsilon of z lambda. So if I restrict my attention to terms with powers of epsilon up to epsilon to the power 7, then the degree with respect to lambda is going to be at most 14. Which means that when I solve iteratively, I just need to compute the first 14 terms of the iterations. So it's a finite process. Okay? Good. Anyway, why is this true? So it's again the same equation and the same reasoning, but with different numbers. So so what do I want to do? Right, so let's write the degree with respect to the variable zb in each of the terms that appears here. Okay? Here it's at most m. Sorry, and I'm working by induction, so I'm assuming I've proven the statement for m, and I'm trying to deduce it for m plus 1. And when m is equal to 0, c of 0 is just e, and that is, and then this is already given. I mean, the thing written here is the thing written here for m equals 0. So, namely for the part that's independent of lambda, so this term disappears. Okay? So I'm assuming the statement is true for Zm, and I'm proving it for Zm plus 1. Okay, so here Zm has degree k in epsilon for some k, and degree m in lambda by definition. So its degree in the zb variables is at most 4k minus twice m. So it's at most 4k minus twice m. But then I differentiate twice again, so minus 2. Okay? And here I get 4k1 plus, minus 2j minus 1, because I differentiate once, plus from this term I'll get 4k2 minus twice m minus j minus 1. And when you add these two, you get 4k1 plus 4k2, but k1 plus k2 is the overall degree in epsilon. So that's 4k minus 2j minus 2m minus j, so that's just minus 2m. And minus 1 is minus 2. So these two terms are of the same degree, and that's their degree. But that's exactly what I wanted, because here the power of epsilon is going to be still k. So 4k minus 2m plus 1, and that's exactly that. Okay? So again, the moral is this is a finite computation. So the overall moral is that if all of our generating functions are of the form a scalar times the exponential of a quadratic plus a perturbation, so the quadratic is independent of epsilon, and the perturbation starts with, is a power series in epsilon which starts at k equals 1, and I artificially crop it at some finite degree, then all computations, so the composition of two such things, can be, and also assume that this is a docile power series, so the degree of pk is less than 2k plus 2, then all computations, then the computations are finite, and in fact can be done in polynomial time. So I could estimate what is the polynomial, but it's not worthy of our time right now. So why? Basically, you use lemma 1 to get rid of the quadratic piece of Q, right? With respect to the variable ZB, Q is quadratic plus linear plus scalar, but the scalar is swallowed here. So you use lemma 1 to get rid of the quadratic piece. You use lemma 2 to get rid of the linear piece. And the cost is the computation on the right-hand side, which are just matrix operations and substitutions, so they're relatively easy operations. And then you use the synthesis equation to solve, to find the perturbation part of the output. And to do this, you have to iterate a finite number of times. In fact, the number of times is twice $k. So finite and not so large. So you have to iterate a fixed number of times performing this calculation. And this is a calculation which happens in finite dimensional space. So the space of polynomials that are, so Zm is some, you know, if you look at the coefficient of epsilon to the 3 here, then it's a polynomial of degree at most 2, 3 plus 2. So I mean, these things all live in small spaces, and differentiating them is a quick operation. So basically everything is polynomial time. Okay, again, I could be more precise, but that's not the time.
Just a quick question.
Yeah.
So you truncated most of the things, and I would like to know if that doesn't contain any information that is useful.
Yes, it does. So I'm trying, okay. So I mean, everything is polynomial time computable, provided I truncate at the finite k. Potentially, I lose a great deal of information, but that's the trade-off. The trade-off is, you know, I mean, maybe there is a lot of information that's unreachable. What good does it do me? So I crop at a certain place, and then it becomes computable. Okay? Okay. So now in principle, okay, so now, okay. Now I just implement everything. Okay? And there's not much time, and I do want to go through this implementation. But so I'll jump over a few technicalities and then go back to them a minute later. But the point I want to emphasize is that often implementing is easier than explaining. Often often implementing is actually really, 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 really easy. I mean, everything I said so far might have sounded complicated. But the actual implementation is just 5 lines of codes or something. So, I mean, there are lots of lines of codes that have nothing to do with, that are kind of formalities. And let me quit all the formalities and get to the point where the actual implementation happens. So, the main routine is called zip, and you zip you zip relative to some list of variables, v's, a quadratic form f, so the matrix f, against an expression e, and the way you do it is you do it in 3 steps: zip 1, zip 2, and zip 3. Zip 1 corresponds to lemma 1, zip 2 corresponds to lemma 2, and zip 3 corresponds to this calculation that had to do with using the synthesis equation. Okay? And then, so here is lemma 1 repeated. So when you want to zip f against an expression times a Gaussian, you do blah, blah, blah. So again, I will go over it later, but the point is, it's very, very easy. You set I to be the identity matrix, you set F to be the matrix generated as a table of coefficients of calligraphic F. So basically this is the matrix F that appears here. Then G is the matrix of partial derivatives of Q, of the quadratic part. And then all you do is you basically, well, you write this determinant, and you look at and you leave yourself for later the operation of and then you. Sorry, what do I want to say? Yeah, maybe you know what? Maybe I'm trying to interpret the formulas a bit too early. What I want to say is that all that appears in the formula are the formulas from here. So here is the determinant of here is this determinant, and this has moved to here. Okay. Likewise, lemma 2. So lemma 2 is how to deal with a linear term. So again, you make you figure out what the matrix F is. You generate a vector uppercase Y, which is just the vector of these coefficients lowercase y. So it's the derivatives of the quadratic term, the quadratic form with respect to the variable z. So it's just a table of the derivatives. And then you, again, if you look at these formulas, they are exactly the terms that appear here. And finally, zip3 is solving this system, is finding z sub lambda by iterating this operation. So basically, you set z0 to be the input, the perturbation term, and then as m goes from 0 to twice $k, the place where we chop, you set zm plus 1 to be, well, this is literally the formula that we have on the board. And then the output is, so z3 is, so I really want to know the output. I don't want to know what z lambda is. I want to substitute lambda is equal to 1 at the end. So, so zip3 just gives the sum of all the zm's where m runs from 0 to twice $k. Oh, and finally you substitute all the variables to 0. Because I want triangular brackets, not the square brackets. So basically, the engine, the big part of the program is the hard part of the program is applying the three lemmas, and it's really, well, it's easy at the end. Okay. So you know, since we don't really have time to go through everything, I'll just very briefly go through what we will go through next time. So here are the basic tensors. So essentially the multiplications, that's the interesting one, and this is, again, these are formulas that you've seen. And then comes the hard part. So I want to see if I can perturb R. So I write and this actually takes relatively a lot of effort, is I write a bit of code that generates all docile polynomials with undetermined coefficients. So I just write, you know, before I had examples of docile polynomials, I just wrote code that generates all docile polynomials with coefficients Ci, where Ci is yet to be determined. Okay? And then, so I set R to be, well, the original R, to which I add generic combinations with coefficients Ck of the all docile polynomials. The details will come later. And the point is that, and then I write all the Reidemeister moves. So here is Reidemeister 3, a product of 3 R's multiplied one way is equal to a product of 3 R's multiplied in another way. Here is Reidemeister 2, here is another version of, no, here is C is the inverse of C bar, here is another version of Reidemeister 2. Basically all the Reidemeister equations are written here. And then I simply solve for them. I now have a system of, a large system of equations with unknowns. The unknowns are the coefficients of the docile perturbations. I mean, later we will have rational ways to discover what the CIs are, but now I'm just brute forcing it. So I'm just finding what they are. So I write, I'll solve all the equations relative to all the unknowns. I'll get the solutions. I'll end up writing what the resulting R and C R's, and then I can start computing. So I'll get knot invariants, and in fact, it will turn out that the result is actually stronger than what we had before. And once this is done, I can raise k, so I can set $k to 2 and repeat. And again, figure out what are again, solve using undetermined coefficients, and then do knot theory at k equals 2. And in principle, I could continue, except at some point it gets too slow to be useful. Okay, but this will happen on Friday, so let's stop.